Right, hi everyone. This video is going to show you how to take a circuit that you've designed as a circuit diagram in Circuit Wizard and the process that I would follow anyway for turning it into a printed circuit board. And obviously, hopefully by now you know that a printed circuit board is one that you could actually solder to and build in real life and put into a product. Whereas what you're looking at the moment is just a diagram, which is kind of a representation of the connections, but not how it physically looks in real life. So by this point you should have a working circuit, much like this one here. So all I've got is a simple timer circuit driving a decay counter, and this could be used for maybe a dice. So it streams through these 6 LEDs, and when you let go of the button it stops on 1, and if you make it fast enough, whatever, it has the illusion of being random. Okay. So you've made your circuit. Obviously I appreciate, depending what project you're doing on my course, or even if you're doing the same project as other people, you're going to have differences in your circuit. Everyone's diagram is going to be different, so all I can show you in this video are the kind of general stages. I'm afraid the intricate bits of figuring out where and how to put certain connections, you're just going to have to persevere with that on your own, trial and error until it works. The good thing about Circuit Wizard though is once you have built it in PCB layout, obviously I've got nothing here at the moment, but once you have built it, so long as you've connected everything together correctly, if you press play it should still work and be simulated in PCB layout, so you can kind of prove that what you've done is correct. Okay, so right, here we go. Check your circuit works. Hopefully you've also breadboarded it as well in real life to prove that all these connections that you've guessed on the diagram actually do what they do on the screen, because sometimes you get discrepancies between the computer and real life, but hopefully some of you have learned that already. And when you're happy your circuit is good, you're going to do the following steps. So step 1, you're going to get the computer to generate a version for you, and you do that by going up to Project, Circuit Symbols, Convert to PCB Layout. And you'll get this little wizard appear, and you basically just click through it. I tend to pick, doesn't really matter to be honest, because the computer can never figure it out properly anyway, but I'm going to go with single-sided normal tracks. I apologise, I'm losing my voice at the moment. Click next. It doesn't matter, you can, to be honest, just leave all this as it is and convert. And what the computer does is it goes and finds all of the components, but you'll notice they're actual real life versions of the components now, so chips look like chips, LEDs look like LEDs, and it's using some crazy maths to try and figure out how to hook them all up as per your diagram. Now the problem is the computer is not as smart as a human, shocker, and it can't figure out all the connections. So it says here we've figured out 74% of the connections. Now obviously that's no good, that isn't going to work. I don't know if you can make it out on your video, but all of these very faint green lines are connections that the computer knows needs to exist, but it just can't figure out how to get from here to here without crossing any lines. So that's going to be your job now, I'm afraid. Other issues with the computer's version: firstly, it's really big. There's a lot of wasted space, like this big area up here and here, so that's bad. It's not in a very logical layout necessarily. So the chips are sort of facing the wrong way, and you've also got lots of what I call flying wires. These blue wires, to be honest, are not always necessary. It should be possible to build a lot of your circuits without using any jumper wires like they've done here, just getting creative. So we don't like the computer version, and I'm not going to accept from anyone in my class just going, oh well, the computer figured it out, I'm going to make that one. You're going to have to do it yourself. And you're going to have to prove to me you did it yourself. So your first job is to copy a picture of the computer version. So just drag a box around it, right click on it, go copy, and just go and paste that into a PowerPoint, like so, and just leave it there. Alright, what we're going to do as we go through this, and this is what you're going to hand in to kind of prove you did your own circuit board, is you're going to have screenshots of you making it as you go through. So first step is the computer version, which is obviously pants here. So, right, you've got your computer version, you've got a screenshot. Next step, I want you to delete all of the connections the computer made, but leave all the components behind. So, start by deleting the background. You can just click them by the way, and press delete on your keyboard. Delete all these tracks. You can get rid of the blue wires. Okay, but what you're doing is leaving the components behind. Now, you may find it useful at this point to click on normal up on the left here, because that allows you to see what's underneath the components. So you can see there's lines here we might want to get rid of. So I'm going to do those. So this is your next stage. Delete everything except the components. Obviously some of you are going to have different numbers of components to other people. Okay, this will be a little bit dull in places. I may well pause the video and sort of come back as and when I've done different steps to speed things up a bit for you. Alright, so you've deleted all the connections. Now you'll find you can't select these green lines and delete them. It's a kind of a glitch with Circuit Wizard, but if you drag a box over them, they go purple and then you can delete them. Okay, so try and get rid of these green lines if you can, like so. If you've got one like this that goes between the chip, you'll obviously notice if you drag a box over it, it selects the chip and the line. So if you hold down Shift and click on the chip, that deselects the chip but keeps the line selected, and you can press delete and get rid of that. Right, so now we've got all our components. Before we take another screenshot, what I want you to do is try and organise them in a layout that's roughly similar to your diagram. So what we've got is the battery on the left, on and off switch, resistors, capacitor, timer, decade counter, LEDs. So I'm going to try and put things in that order. So here's my battery, let's put it there. My switch was kind of in the top right, so this is what I'm going to solder my switch. I'm doing this from memory because I'm that pro. Right, there we go, capacitor, variable resistor, normal resistor, so that's kind of laid out a bit like that. Then the timer, then a switch, a resistor and a switch. So here's the timer chip. I'm actually going to rotate it left, and I'd encourage all of you, with your chips by the way, to rotate them so the notch is pointing left. You'll see why later on, but basically if you do them that way it means that the positive connection points up and the negative connection points down on all the chips. It just makes it easier to wire things up. Right, LEDs all go on the right. I'm going to stick them over there. And then I had a switch and a resistor sort of between the timer and the decade counter. So I'm going to do that next. Okay, so I've roughly kind of laid it out as per the diagram. I've got a random red blob there that I don't need, so I'm going to delete that. And the other thing I'd encourage you to do is make a bit of space. Always a good idea, because you'll find out that when you start making connections, if you don't leave yourself enough room to start with, you actually make your job harder. It's best to build the circuit but large and then start to shrink things down afterwards. That's what I find. Alright, so just also check that it's in kind of input, process, output order. So inputs, battery, switch, capacitor, resistors. Processes are in the middle, that's the two chips, and the outputs are on the right. So that's your good starting point. So I would get a screenshot of that now. Again, drag your box around everything, copy, and stick that in your PowerPoint ready to write up later. Okay, so that's stage 2. Right, stage 3 is when it starts getting a bit harder. You've now got to start connecting things up. And there is no easy way to do this other than to be methodical. So I tend to start with what I call the power rails, as in the positive rail and 0 volts rail. Now, if you've done breadboarding with me and you've built a circuit with me before, you should know what I mean by positive. The positive rail is anything that connects directly back to the positive of the battery with nothing else in the way. Obviously on here there's a switch in the way, but that's just a power switch, so it doesn't really count. And then 0 volts is anything that goes directly to the 0 volt end of the battery with nothing in the way. So right the way from here all the way down there, that's all connected to 0 volts, including that. If that made no sense to you, don't worry too much, just kind of watch what I do. So PCB layout. I'm going to draw in a positive and negative rail, so I'm going to go up and get my track tool. Here's my battery, plus and minus. At this point, by the way, I would encourage all of you to go down to the bottom right of the screen, click on this thing, and select 0.025 inch. That makes the grid smaller, and it means you can draw things a lot more accurately without the cursor jumping left and right. So, I'm going to draw a nice big long positive rail, like that, and I'm going to draw a nice big long 0 volts rail, like that. I could well shrink this down later, and I will do, but for now I'm just putting them in. So I've done a kind of line representing this and this. I'm then going to start with the chip and stuff and kind of work my way down methodically. Right, In fact, before I do that, sorry, I am a bit ill at the moment, so if I'm not making a lot of sense, I do apologise. We've got a switch in here that I need to put in, and the switch is immediately after the battery, before the main positive rail. So that was our on and off switch. I'm going to go and put that in here, so delete that, and take my wire and just put my switch in the loop. Now, just on this note, you might be looking at that and thinking, well, that doesn't look much like a switch. If I look at it in real world, that just looks like a weird block with screw holes in it. Well, that's because you've got to remember we're now working in the real world. We're working with actual components, well, or representations of them. So you would actually be soldering a switch on wires to here and soldering a battery to here. So what I'd like you to do, just this will remind you while you're here, this is why you've got these PCB components and off-board components, or as I like to call them, on-board, off-board. Off-board is anything that goes on wires, so we know our battery, we're probably going to use a 9-volt battery, it's going to be like this, it's going to be on wires, and we'll find it under off-board power supplies, 9-volt battery. And we would actually solder this to here and here. So that's your first thing in Circuit Wizard. Remember, anything that's going to be on wires in real life also needs to be on wires on here. Likewise, our on and off switch, that will be under off-board switches, and it wouldn't be a push switch because then you'd have to hold it down while you were trying to power the circuit. It would be a latching switch, so maybe one of these again, and we just drag from here to here and we'll put in our on and off switch. Okay, so you're starting to see that actually just because you've got blocks there, these are just the areas you solder to, and you've still got to put wired components on. Right, now to make the rest of the connections. So we've got a 1K resistor here, and one end of it joins to positive. So this is a bit like breadboarding. Here's our 1K resistor and it joins to positive, so I'm going to put a connection in there. That 1K resistor joins to a variable resistor. Here's our variable resistor, here's our 1K, let's join them together. Now again, you're going to come across problems like this, so any of you who are using a variable resistor, you'll notice that in real life the variable resistor has 3 legs, yet on here it only has 2. You only need to use 2 of these legs on the actual PCB mode, and you should always use the top one here called the wiper and either of the bottom ones. Doesn't actually matter which, all it does is affect which way you turn it to increase resistance. So I'm going to pick the right hand leg, and just to check where it went, the other leg of the variable resistor joined to a capacitor, and it joined to the plus end of the capacitor. So here's our capacitor, you can see the little plus symbol, I'm going to join that to that. Okay, and try and use nice straight lines as well. Right, other end of the capacitor went to 0 volts, and because we put the rail in there, we can just go straight down to it, like that. Okay, so I've done this kind of pathway there, which is this whole bit there. Now obviously there's a bit more missing. I've pretty much done all of that bit so far, but I have got between pin 7 of the 555 timer and between the resistor and a variable resistor I've got a connection. Now this is where things get confusing. The chip here is put in a nice, all the legs are in the kind of position they need to be to match up with where they need to go to. But in the PCB mode, they're in a totally different place. So pin 1's on the bottom, 4 and 8 are at the top. In real life, that's how a timer looks. It's totally different. And you'll notice if you hover over the legs, and you should know this from breadboarding, pin 1 is always to the left of the notch, so that's pin 1, pin 2, pin 3, and you notice it also tells you the name looks, so that's called output, nut reset, control, pin 6 is threshold, pin 7 is discharge, pin 8 is power. And it's the same on here. If you hover over these bits, look, power, 7 is discharge, 6 is threshold. Okay, so they are the same connections, they're just laid out differently. So this is where most people go wrong. They try and make this look exactly like that, as in they would join to the nearest leg, but you're not doing that. You're more interested about what number leg it goes to. So we're trying to go between these two things here to leg number 7, and leg number 7 is this one. Okay, so I'm going to do that, and I'm deliberately going to make some problems here so you can see how I'd get around them. So that's 7 done. 6 and 2 joined together, so here's pin 6, here's pin 2. Now a lot of people, right, most people naturally will probably just do this. Here's 6, here's 2, right, and 2 and 6 also go between the resistor and the variable resistor and capacitor. So here's the variable resistor and capacitor. 6 and 2 need to go there, so they'll do this. Right, and then they'll be pretty happy with themselves, and they'll go, great, I've done that, I've done that. Now I've got to do pin 1 to negative, or 0 volts. So pin 1 goes straight down to 0 volts. Here's pin 1, and this is where things start to get a bit harder. Well, there's 0 volts, and a lot of people go, well, I could do that, but if you do that, you've broken the golden rule of making a circuit board. You cannot have a red track crossing another red track. Because they're both made of copper, when you actually make this thing, they'll be connected and you'll ruin it. So we've got to find another way to get to 0 volts. And this is where people forget that you can actually go through the middle of components. You can go through here, like that. That's exactly the same thing. You can use one component as a bridge over another. All you can't do is cross red tracks. You could, if you wanted, also do this. You could come down, stop, come down, put some pads on there like that, blue one, and then get from this little menu a flying wire and make a little jumper. Now that's one way of getting you out of a really sticky situation, but it's bad practice because that means you've got 2 extra holes to drill, an extra piece of wire to cut, and 2 extra things to solder, so that would add to manufacturing time and cost. So really, if you can avoid it, you should try and find a direct path back to 0 volts. So let's just do that for now. Now I actually know for a fact that my this layout can be improved upon even more, but I'm going to show you how to do that in a minute. So pin 4 and 8 now need to go up to positive. This is the positive rail, but they need to go to the bit of the positive rail that's after the switch. So here's the switch, this is the positive rail after the switch. Right, 8, we can't go up that way because we'd be crossing, but we could come through here, like so. And now we're starting to get, things are starting to get even harder. We need to get pin 4 up to positive, and this is pin 4 here. Now we can't go through here, can't go through there, we'll cross, but we could go through the middle of the chip. Okay, so that technically would work for all of those connections, except we've got one left to do, which is pin 3 has got to go to pin 14 of the decay counter. Here's the decay counter, here's pin 16, 15, 14, and we need to get that to pin 3. Now we're really stuck. How the hell are we going to get that to here without crossing anything? We can't go through here, we can't go anywhere. Please don't be tempted to try and go through the middle of the chip like that, because you're going to make connections. So at some point you may have to admit defeat. However, I know there is a way of doing it without crossing any wires. So what I'm going to do is pause the video, and then I'm going to show you my reconstructed method without boring you by making you watch it. And you'll see that actually with a little bit of creative thinking you can do the same connections and have that wire available. So let's just pause it. Right, as if by magic I'm back, and just to prove to you it's possible, I've done it. So we've got 8 and 4 going to positive, 1 going to negative, 6 and 2 joined together going between those, 7 going between those, and pin 3 is available now to go to pin 14. You can check it if you want, but I promise you that will work. So we've made that part of the circuit. What's quite cool now is if you want, because we've got this powered up, or if you've got a timer, or if you've built part of it, you can start to test bits of your circuit. So if we look at current flow, and I press play, you'll see at the moment the voltage, the red colour, is only travelling as far as the switch. If I turn the switch on, we're now supplying voltage to the timer bit, and you can see pin 3 going red, green, red, green, red, green. I can slow it down by making this resistor bigger. Well, just a little bit, red, green, whatever. Okay, and I can kind of prove that actually that whole part of that circuit works now. All I've got left to do is build the right hand end. Now again, I'm not going to bore you by making you watch me build the right hand part of the circuit. I'm just going to build it and show you it finished, and then talk you through the next stage of what you need to do with your projects. All I'm saying is I recommend as you build bits, if you can test it at different stages, then test it. you know the timer circuit should be making a pulse. So when you've built the timer bit, as in this bit here, why not see if it's making on and off pulses? Right, I'll be back in what seems like no time at all once I've finished off these other connections. But it really is the same method. Look at where things join and join them up. The only thing I need to mention is that this chip here in Circuit Wizard, in the diagram it doesn't give you an option to draw in the power and ground connections. Now if you look at the actual chip, this pin 16 and that pin are power and ground, and they need to go up to positive for power and down to 0 volts for ground. Now annoyingly, Circuit Wizard doesn't draw them in the diagram, and everyone forgets to connect them up, as I guarantee half of you lot will. It's the same whether you're using a 4017 or a 4026. You must go and put in that connection and that connection on here, because they won't be there on the diagram, and otherwise it basically in real life this chip won't get powered and it won't work on here either. Right, I'll be back in a minute once I've finished it. Right, actually I came back a little bit early. I realised it was important to tell you that again, because these chips are laid out in a nice logical order, look, output 0, 1, 2, 3, 4, they're all in a nice order on here. Annoyingly they're not in that order in real life. So for instance, well, you can find out, look, if we hover over output 0, in real life it's actually on pin 3, as it says there in that label. Output 1 is on pin 2, output 2 is on pin 4, output 3 is on pin 7, output 4 is on pin 10. You can see they're in a totally random order, so my LEDs would need to be hooked up in the orders of pins 3, then 2, then 4, then 7, alright, and so on. Okay, so make sure when you're looking at this diagram you hover over the square, find out what pin that LED actually is on in real life. So I'll just do this one, then I'll pause it and come back again. So this first LED is actually connected to pin number 3 on the diagram. How do we find pin 3? Well, there's the notch, there's pin 1, 2, 3. So our first LED is actually hooked up to that. Okay. And the other end of it went to 0 volts, so we'll put that on. Okay, I'll pause it, and I promise I'll be back this time when it's finished. Alright, as promised, I am back, and here it is. Now, you might be thinking, yeah, I finished. No, you haven't. I'll tell you why in a minute, but this is your next stage for taking a picture for your lovely little diary. What we've done now is we've successfully made all the connections, and we can prove that. I've had to use one flying wire. I would say using up to maybe 2 or 3. Some of them you can do in none. Some circuits you might need 2 or 3. If you're using more than about 3 flying wires, you're not trying hard enough, basically. But already this is miles better than the computer's version. First of all the connections have been made, unlike the computer that only managed 73%. Secondly, it works because all the connections are made. You can see if I'm holding down the button, everything works. And thirdly, I've only used one flying wire, and the computer had used about 5, and if we have a look at here we go, the computer had used 1, 2, 3, 4, 5, 6, and it didn't even figure out all the connections, so already we're a lot better. Now, that's a good time for a screenshot. Once you have powered it up, proven it works, look, power on and off works. When I hold down my push to make button, it rolls through them. You'll have also noticed, by the way, I went and got an off-board push to make to connect up to that connector there. I can check that my time delay changes. There you go. Like if I change that resistor that way, it got faster. If I change it this way, it should get a bit slower. What you'll notice, by the way, is the LEDs don't go in a nice order anymore. They sort of skip left and right, but they do all light up, and that's because, remember I told you these outputs aren't in the same order in real life as they are on here, so it's kind of going like 1, 2, 3, 4, 5, it's skipping back, right? If you think about that though, that doesn't actually matter, because in real life you're going to be putting your LEDs like this. You're going to be getting them as an off-board one, and you're going to be putting them on wires and wiring them up to your to your circuit board. And if they're on wires, then you're free to place them wherever you want in your box. So all I'm saying to you is, just because they're in a messed up order on your PCB doesn't actually matter for real life. Doesn't actually matter when you make it into a product, because you can just put them on the wire and place it where you need to. It might be a good idea though just to number them, which one is 0, which one is 1, which one is 2, and you'll just find it easier to put your box together. Anyway, we've proven it works. which you should have done. There's no point taking a screenshot until you know this works. So when you do know it works, highlight it, copy it, and put it into your PowerPoint. Now I'd imagine for most of you, if you're doing the double lesson today, that will probably be about as far as you manage to get in the double lesson. If you manage to get it converted and working in big, then that's great, well done. Make sure you save this PowerPoint with all your screenshots. What I'm going to do is record I'm going to carry on with this video, so obviously if the lesson's finished, then yeah, pack up, go to break, whatever. But if you've got further ahead or it's the second lesson, now you need to know how to compact and make the circuit board smaller, which I'm going to talk you through. So here we go. Right, we could make it tinier in a lot of ways here. There are lots and lots of wasted space on this project board, and the way I like to shrink, well, first of all, the reason we need to shrink it down. Firstly, it gets you more marks when you do your coursework because it shows you've been efficient with materials. Secondly, if you were actually manufacturing this, it would save you money. Every little bit less board you need is less copper material wasted, which means less money spent buying it. It means you can make more in one production run. Every flying wire you reduce means less soldering and drilling to do. So reducing and shrinking and minimizing flying wires is what anyone manufacturing a PCB in real life would try and do. Anyway, so we're going to try and compact this down. Now, I tend to start from a chip and in the middle and work from the middle out. So I'm going to start here. This is already pretty compact in here. I can't really get any closer than that. My rule would be in Circuit Wizard always leave the width of a track, so how wide this red bit is, between tracks. Don't get them any, if you put them that close, you'll find when we try and make, if you zoom out to 100%, look, so this is actual size, they're starting to look very close, and our photo etch tank at school will struggle to erode away the gap there. So anyway, starting from the middle, I could drag this and bring it down. Okay, that's made that bit a lot smaller. I could start bringing these in now, so I'm going to bring this resistor right over here and down a bit. Remember where things were connected, so that was connected to here, but then this is the same as this, so I could just do that straight down, and that's the same connection. Alright, and I'm just kind of gonna, I might figure out a way to speed this video up in the future, so you can watch this kind of accelerated like a time lapse, but I'm not smart enough to do it at the moment. But just kind of watch what I'm doing and you'll kind of see how I'm starting to shrink things. So this is connected to here, which is that. So actually that can just be here. This can all be drastically shrunk down now. I'm afraid this bit is time consuming. It does take a long time. But tough. That just shows perseverance, doesn't it? Dedication to your electronics cause. There we go. Look at that. Right, so I've brought those two things closer. It's a good idea, by the way, as you start changing things, just to press play every now and again and just check, does it all still work? That just improves you haven't broken any connections. If you did break them, just do Control Z, you know, and undo to a time when it did work, or Control Y, redoes, redoes. You know what I'm talking about. Right, let's bring that capacitor up. So what I'm trying to do now is pull, imagine the chip is a black hole and I'm trying to pull everything in towards it, but without them ever actually touching. That's what I'm doing. So I'm bringing the capacitor close enough that it's not overlapping, but as close as I can get it. Right, I've done that much. That then means I've got all this space here, so I could pull my on and off switch in right up to there. Let's just preserve the connection. So that was as far as there. You have to be very methodical and really keep your eye on the ball. This joins onto that. That now means I can pull my entire battery in to here, but that's going to collide, so I'm going to move it up a little bit. Okay, and that joins onto there. Right, now just with about 2 minutes work, I have saved easily a quarter or a third of the width of that board straight away, just by doing that. Now the world is your oyster, really. What I'm going to do is pause it again and just show you how small it can be made, okay, with a bit of effort. The rest of it, for you, it's down to you on your circuit board to shrink it. This I would still not be happy with. This is still too much wasted space, so Tune in just a second for the improved version. Let's pause it. Alright, this video is getting very epic. We're at 30 minutes already. There you go, proof. So that took me about another 5-10 minutes in real time to do, but I've now shrunk it down to a lot more compact size. So if I zoom out, this is 100%, so if you're playing this full screen, this is actual size of the circuit board, which is pretty good. Still works, on and off, still counts through. That is much more in line with what I'd be happy to build. If you just hand me in a huge circuit board that you've clearly made no effort to shrink down or not reduce the number of flying wires, then I just won't manufacture it, because I'm not going to waste the school's budget and materials trying to do it. So do make your best effort to do this, otherwise you're going to have to build one of the generic boards and you won't be able to get a very good grade for your work. Anyway, right, you might be thinking, am I finished now, Mr. Winter? No, there is more to do. Very sorry, but yeah, we need to add to this even more. Several things. We're going to start improving this to make manufacture easier and more reliable now. So these, but this would be a good stage for a screenshot. So again, now you've shrunk it and it still works, grab yourself a screenshot, put it in your PowerPoint. There we go. So we're building up a kind of little history of proof of what we did, and you can actually see size for size now. If I get those batteries the same, just how different in comparison. That's probably a quarter the size of that as it was originally. Much better. That would mean 4 times more profit. There you go. Anyway, what we've got to do now is make it better for manufacture. Now, several things I'd like you to do. If you've got LEDs and you're going to use off-board LEDs, like most of you will, as in you're going to put them on wires like this, I would like you to go and get things called terminal blocks, which you'll find, what am I doing? Under PCB components, connectors, terminal blocks. No, click the wrong one, sorry, my mouse is really bad. There we go. And replace your LEDs with these. Okay, so for instance like this. I'll pause it and come back when I've done it to save you the aggro of watching. Alright, there we are. Reason I'd like you to do that with LEDs in particular is because if you look at the size of the pads on a terminal block compared to an LED pad area, it's much easier to solder to this big round area than it is to these. The other benefit is they're spaced slightly further apart, and LEDs, if you put them directly on the board as this picture's designed to, they're very close together and you'll find the soldering iron will bridge them. I'm doing this to help you. I'm trying to make your soldering life easier. It also gives you some other options as well, like if you use a terminal block, you've opened up some new pathways. So I'm not saying this matters here, but for instance, you've now got a big enough gap that if you needed to route a wire or a track through the middle of something like that, you could do. Okay, so it gives you other options, and because you're going to be putting your LEDs on wires anyway, you're going to be doing it like this. So hook up your wires as they would actually be. Again, I'll pause and come back when that's done, but all I'd like you to do is make sure you change the colours of the wires for what you would do in real life. So you know my good practice is to use red and black for positive, so long leg is positive, so right click on the wire, colour, go red, and on here go black. Okay, bring your LED out as far as you want it. Right, I'll pause and come back when I've done all of those. Alright, so that's that done, and again let's prove it, check it still works. Good, and now it's cycling through the LEDs as it should do. You'll notice one of these LEDs is not lighting up though. I'm not entirely sure what that is. It might just be a glitch with Circuit Wizard, but I'll figure that out later anyway. So check everything still works, check the colours are right. That's still not ready for manufacture, because now what we need to do is put borders and labels on. And the reason we need to do that, if we go to artwork view here on the left, that is actually what your circuit board's going to look like when it's manufactured in copper. Kind of confusing. When you look at that, it just looks like a bunch of holes and you don't know what goes where. I've actually now discovered why that LED wasn't working. I'll just fix that. There's a track missing here. Right, so we're going to use the border and label tool now to spice this up a bit. So first we'll do the border. If you go up here and click Circuit Board and just drag a rectangle around your object, That gives you a nice border to it, and if you go and look at real world view now, you'll see it's actually put a background on it. Okay, so that shows you where the limits of your board are for when you're sanding it. Let's just check those LEDs work. Yeah, all fixed. Right, and labels. So back to artwork view, you'll have to kind of flick between these here. Right, we know that this is our battery connection, and this is positive and this is minus, so what I'd like you to do is label that. It will help you when you get in the workshop when you're putting this together. Plus and minus, make sure you stop it, by the way, if you're trying to do anything else. Use the label tool up here, and you can type in plus V, put that next to the positive connection, and 0V. So now we know where to solder the positive and negative of our battery connector. Again, don't be afraid to make yourself a bit more room if you need it. If you want, by the way, if your labels are too big to fit where you want them, you can right click on them, go to font. Oh god, why is this going slow? Okay, and you can choose a smaller font size. You can actually type in numbers lower than 8 as well. Okay, I wouldn't go too small with it, because remember, by the time you zoomed out to 100%, the writing's going to get tiny. Basically, I'd like you to go around then and label everything else on your board and put your name on it as well. So I would expect you, for instance, to be labeling plus and minus for all of the LEDs. You should label the values of the resistors, so I'd put 1K, 10K, the capacitor, label it plus and minus. You could label on and off, you could label pin 1 of the chips and put your name on it. So I'll pause it and I'll come back with a fully labelled board, and then that really will be the final bit you need to do, assuming it all works. Okay, and finally here we go, the finished article. So just to show you the sort of labels, I've put my name on it. By the way, you'll notice everything is written back to front with the label tool. That's intentional, because when we print it out it has to go in back to front in the light box when we manufacture it, so don't worry about it being back to front. It's actually deliberately done that way. You're looking through the board in Circuit Wizard. I've done all the pluses for the LEDs. I've labelled P1, P1 for pin 1, push to make, 10K variable resistor, 10 UF plus. Alright, I've labelled the hell out of it. The only other thing I've put in is two, if we look at it in normal view or real world here, I've put in 2 big pads here using the pad tool for strain relief. And you might remember from our previous projects, things like the battery wires tend to be very weak, so we loop them in and out of big holes on the board and then solder them. Obviously I can't show that threaded on Circuit Wizard, but I've left it in my project for better quality control. So if you want to put those in, all I did was get the pad tool up here, right click on it, go to properties, and I set the width and height to 0.2 of an inch and the hole to 0.1. Okay, and then I just copied and pasted that. So if you've got delicate components like buzzers or battery clips, put yourself some strain relief holes on some blank space on the board. Okay, final, obviously check it works still, which I'm confident it still does. There we go. And my final thing I'll remind all of you to watch out for, remember that labels will actually be made in copper as well, and it is possible to ruin your circuit by accidentally joining things with labels. So if I had put this plus here, for instance, it's actually acted as a bridge, and it's a very easy thing to miss. But if I press play now, no, it still seems to work, because I don't think Circuit Wizard realizes it's a problem. But in real life, that would be causing a short circuit across your capacitor. So always make sure your labels are not bridging one track or component to another. So just like red shouldn't cross red, labels shouldn't join one bit to another. Okay, right, take your final few screenshots. So for your final few, I'd like one like that in real world, all neatly laid out with all the labels. Put that in your PowerPoint. Okay, make sure you put them in the order that they happen so you don't forget what went on. And then your final picture I'd like is an artwork view but zoomed in a bit. So just that. So and that allows me to see all the details when I mark your work. Okay, right. I know that was an epic video, and I hope it helped you. Hopefully, I appreciate you're going to have loads more problems because you're all doing totally different circuits to the one I did here, but the methodology is the same. Do it in those stages that we did here, and just be thorough. If something doesn't work at one point, go back and try it again, and try it 100 different times until it does. You'll never get good at this unless you persevere. So if it doesn't work first time and you give up, that's your tough luck, I'm afraid. There is no simple way to teach you this other than to keep trying it over and over again in different combinations. Alright, electronics is all about being super accurate and super organised and really thorough. And if you're a person that likes to rush things, as I am sometimes, it can get really frustrating, right? But do persevere. This is one of the hardest courses and things to learn that we do in technology. So anyway, there you go. Right, I'll be interested to see what you can come up with.